linear wave solution, which of course all of you know. And now let's consider the nonlinear theory. So, first step before we do that, right? So, okay, let's remind equation in a Fourier space, right? So, to make a nonlinear theory consistent, I mean, first of all, one has to actually shift frequency. So it's quite a general property, and even observed in a single, one-dimensional a nonlinear oscillator, like a van der Pol oscillator, right? So unless you shift the frequency, your perturbation theory will be inconsistent, right? So it's the same here, okay? What do we exactly do? What is the frequency correction, right? Okay, so we write equation. We rewrite it in the following way. So here, I introduced a new variable that is related to my original variable by the following transformation, where omega k is the linear dispersion relation of a linear wave plus the frequency shift. Okay, and also the summation will be over the original variables, and I put a little prime here to denote that I've already removed the terms such that K1 is not going to be equal to K2, and also it's not going to be equal to K3, right? So the terms with K1 equal to K2 and K1 equal to K3, they are the diagonal term in the sum, right? They make this frequency correction, okay? And as you remember, N is the mass density, so which is constant. So it's a special property of Gross-Pitevsky equation that it's constant. So for some other systems, like waves on water, that can actually be a function of k and some more complicated. But here it's very simple shift. Okay. So this is called interaction representation variable. Okay, so one other thing I have to add here is the is this oscillating term, right? So this oscillating term arises because I multiplied by oscillating factor like this. So essentially, what happens is that I get rid of a linear term like this, right? So all the fast dependence on time is in this factor. So you see, the fast dependence is oscillation with this frequency, then a little bit slower dependence, the kind of first order nonlinearity effect is in frequency shift, right? And then what remains is a slow dependence in this coefficient, right? So if it was a linear theory, then this coefficient would be constant, right? So linear theory corresponds to epsilon equal to 0, and so then AK would be constant. Okay, so this way we separate fast and slow time dependence by this transformation. So now I introduce an intermediate time. So I want to really filter out the fast time dependence and for that I introduce some auxiliary time T, intermediate time, which will not appear in the final formulation. This is just to say I want to filter on the scale which is greater than linear oscillations, and but still less than the characteristic evolution of a nonlinear part. And then I do expansion of nonlinearity, sometimes called Duhamel expansion. So this is a formal expansion in nonlinearity. So I assume that I know the my initial condition at t equal to 0, and I want to find this a case. So I know initial condition, and I want to find the solution by represented as a series in nonlinear parameter, right? So the linear theory is when epsilon equal to 0, right? So then we can say, so if I put epsilon equal to 0, I have this. So the first term, so it corresponds to a linear theory. So which we know corresponds to constant AK, right? It's not evolving, right? So we found that A0 is just an initial condition, right? So then in a term epsilon of order epsilon, right? I have an equation yes, I forgot to actually tell you that what I mean by omega 1k23, it's again shortcut notation for omega 1 plus omega k minus omega 2 minus omega 3. It says keep yes, I have. Thank you. So I mean, it's B here, but I decided to change it to A. Yes. Okay. Okay. So that's omega t, right? Omega, yeah, like this. So now, if you take into account the previous, okay, so what is this, right? So I substitute that into the equation, right? Into this equation for A, and I just count the what I have in front of epsilon in the resulting infinite series in front of epsilon squared and so on. So term by term, I recover that. So I do it by recursive substitution, right? So I do it by plugging, better and better approximations back into the equation, right? So this is the first approximation. Second approximation, I plug that into the equation here on the right-hand side. So I get this term, right? And so I have an equation for A1. But now if you remember that A0 is independent of time, right? So it's just a constant. All time dependence comes from here, right? So I easily integrate that, right? And I have so So I introduced a notation for the following integral. So which is simply so I introduce this notation because I will have to write it a few times so that I keep it short and introduce this notation, right? So simply integrate all time dependence comes from here from 0 to t, so elementary integral to take, right? Okay. Okay, then I do the next order. So in the order epsilon squared, again, I plug the previous order into the right-hand side of the original equation. Yeah? Yes, sure, yeah. Okay. And the I missing somewhere, yeah. So minus I, okay. Thank you. Okay, so you get an idea, right? So what it's like. So now I express everything in terms of A0 by substituting here A1 from the previous line, right? Then again, the time dependence will come only via oscillating exponent. And also this thing will give us time dependence. And then again, I integrate. Okay, so that is quite a simple integral. I'll write out the result. Conjugate, B6 0 conjugate, minus 2 So where I introduced another notation for which I call E. That's, as I told you, integral, time integral, like this. Okay, so I mean, of course, if I keep doing that, iterations, so things will be getting bigger and bigger. But fortunately, the second order is sufficient for me to have the leading order nonlinear evolution. Unfortunately, first order is not sufficient, right? So that I have to keep up to the second order. So now I remind you the goal is actually to derive equation for the spectrum, right? So the spectrum, okay, at the moment T capital, right? So that will be, by definition of the spectrum, so you know that because variable a and psi different only by complex exponential, so the modulus is the same for them, right? Okay. So then I plug in the epsilon expansion in here, right? and open the brackets. So by opening the brackets, I have N0 then epsilon order plus complex conjugate plus the epsilon squared order so A1 mod squared. There will be two terms, AK0 conjugate AK2 right plus complex conjugate. So plus higher order terms, dot, dot, dot. So N0 comes from, mod square of A0, right? Okay, it's just the initial spectrum. So the first order term, it's a cross product of this and that, and plus its complex conjugate, right? And the second order terms, respectively, that one mod squared and this one cross with that complex conjugate term. Okay, so now there was a question, what is the averaging, right? Okay, so now I have to do averaging, and here's the statistical assumption. So it's called RPA, so which stands for random phase and amplitude. So the difference with standard acronym RPA, random phase approximation, right? So here's an important moment, okay, so that actually what is implicitly assumed in derivations, it's random phases is not enough, okay? The amplitudes also have to be random. Secondly, so I borrowed an A instead of approximation, right amplitude, right? But also, by that I'm saying that it's not really an approximation. It's a property of initial field. That what I'm going to take initial field with this property, right? Random phase and amplitude. What do I mean like that? RPA, so this is an initial field. A initial field, as we know, A0, right? So I say, okay, let me represent it as, since it's a complex Fourier coefficient, right? I can always represent it in amplitude phased form. And then I can say that both the amplitudes and the phases has to be independent random variables. So independent meaning at each k, they are statistically independent from each other. So moreover, phi is uniformly distributed takes any values from 0 to 2 pi equally probable, right? So that's so if I just you see, this assumption concerns not only phi's, okay, not only phi's independent random variables uniformly distributed, but also the amplitudes. That will be important. So something that not always realized. So secondly, I notice that this assumption is not equivalent to Gaussianity, right? So it's not always Gaussian, because for Gaussian fields, so the distribution of the amplitudes would be fixed to be a Rayleigh distribution, to be the specific distribution PDF of of these amplitudes squared, right, would be like this. Okay, so and we're not assuming that, okay. Gaussian AK, right? AK variable. So, and that's also important because it means that we can consider non-Gaussian fields. We can consider distributions. What happens if we start with some force and that produces non-Gaussian initial statistics, and how does it evolve, right? But that's not what we're going to consider this question, because that would require derivation of equation for PDF, which is also possible. Now, because the amplitudes and the phases are independent, so the averaging will also be independent over them, right? And how do I do averaging? Let me consider the term that comes in the epsilon order. So you see what that means, right? This means averaging over phases will look like this. So I take the modulus separately, so that will have to be averaged over the amplitudes. But this integral represents the averaging over phases. So I write I, so minus phi 1 minus phi k plus phi 2 plus phi 3 d phi 1 d phi 2 d phi 3 d phi 4, right? So because phase is uniformly distributed, I have to just multiply, integrate over phase and divide by the total phase range, 2 pi, right, for each of the 4 phases. And so you see, taking integral like that, easy to see that, that in most cases, this gives you 0, because this is a periodic function with mean 0, right? Unless this exponent cancels, right? Some phases cancel each other, and they give 0, and then this is 1, and then it gives a non-zero contribution. So, so this is 0 unless, so k equal to k2, k1 equal to k3, or k equal to k3, k1 equal to k2, or k, they're all equal. Right? In which case, this integral just simply gives 1. So this is called Weak's pairing rule. Cancel. The normalization coefficient. Yes, so you see, situations like that, okay, maybe am k equal to k2, k1 equal to k3, so 0, right? So 1, you integrate, so you get 2 pi, 2 power 4, because you have 4 integrals, yes? Divide by normalization coefficient, so that will be given 1, right? So then, okay, so Weak's pairing rule is saying that what we essentially did here schematically, right? We paired, so each of complex conjugate amplitude with an unconjugate, so the original amplitude, pairwise, right? Phi is what? Yeah. Phi is related to k like this. Okay, so so at each k there is a phi, right? So the phase of Fourier coefficient. Okay, so so Weak's pairing rule is telling us that pair A0s with A0 conjugates, right? So if number of A zeros and and conjugates are unequal, right? You can't do that. You can't pair them all. Then you will still remain in oscillating exponent will remain, and the result will be 0, right? Okay, so in this particular case, okay, so these combinations, you see, they correspond to diagonal terms that we removed from the sum, right? So therefore, the result sorry. So then it gives us a zero result because we diagonal terms at the point where we did frequency renormalization, right? So this means there's no contribution in epsilon order. Now another remark, very briefly, this term is usually also, I mean, when you do, one does weak pairing, usually this term is not written, right? Okay, so it's actually where all of them equal to each other, okay? So in this case, it gives 0 because it's also diagonal. But in higher, if I start writing out higher orders, it's actually non-zero. But it does not matter because you see each of these pairings, okay, gets it's more and more restrictive. This very tiny number of terms where you have more indices coinciding, which means in the sum it will be subdominant. If I take limit of continuous limit where number of terms in the sum goes to infinity, I go to the integral, right? So they will be subdominant in equation for the spectrum, but not for equation for the for PDF, which I'm not going to consider here. So in other words, this term would be important if we considered PDF, but we're not considering PDF here. So, and I need to watch time. So. 15, yes, okay. Right. Okay. So you see, so far I've only done averaging with respect to the phases, right? And as a result, what I got is the following thing. Okay, so that was the, so I showed that the epsilon order is 0. So let me then consider the epsilon squared order, and there are 2 contributions, and I will consider this one first. Okay. Once you understood how to do weak pairing in the 4th order correlator, you understand them in general because they're quite straightforward. All you need to do is a pairing. Not B's, okay, I'm sorry. Okay. So, as I told you, so we have to do the pairing. And so in this case, there are two pairings, right? So A1 can be paired with A4. B2 can be paired with 5. And 3 with 6. Or B1 can be paired with 4 again. So B2 with 6. So in fact, I mean, they are equal to each other. I just simply, I can get one from the other by changing index 2 and 3, which is dummy indices of summation, right? So I need to write double. And so you see, and it's important that I'm not pairing the diagonal terms because of here, right? So excluding them. So after such Week's rule, it's called Week's contraction rule. So it really contracts to something much nicer. So now, you see, that's the point where randomness of amplitudes become important, right? Because if I don't assume them, I'm stuck. What do I write for that, right? So I can rewrite it. In a product form. It's independent averages using the amplitude that the fact that they're independent random variables, right? And by doing that, I see that I get expressions that is the spectrum up to 3 factor L over 2 pi to power d. So then what I'm going to do, I'm consider what's the asymptotic value of this quantity when I take the limit of big time. So you see, I take what I wrote before for delta. So mod square it. So this is just this expression. Okay, and you know that because remember I took time to be intermediate time, right? So for example, I can take time to be 2 pi over epsilon omega k, right? So because it has to be less than 2 pi over epsilon squared omega, and but greater than this linear period. So I could take that for simplicity, right? And then I see that as epsilon tends to 0, so this time tends to infinity. Yeah. Yes, yes. But what you want to do, you kind of want to march forward in time. You want to filter your. Okay, just hold 1 second. I will explain that in just a minute. So what I want to say that okay, so this expression, okay, so the reason I wrote here, okay, so in this form, right, so that it looks like a sine. Right? If you plot a graph of it, right? So it will be like looking like this. So it's like a sine, but divided by that. So if I plot it as a function of its argument, it looks like this. So at t equal to 0, right? So I use L'Hopital's rule, and so I have a maximum at t squared. And the point where it crosses 0 is 2 pi over t, right? So, and it's easy, it's actually approximately, right? How can I evaluate that? I say, okay, well, let's replace that with a triangle like this. And what's the area of this triangle? So multiply this by that, and that's the area of this triangle, right? So this is equal to 2 pi, right? So this is kind of this kind of speculation turns out to give a precise answer. This is in fact a table integral to show that that integral of that with respect to omega is 2 pi. But what you also see that is getting 2 pi times t. I'm sorry. Okay, multiply that, right? So, but what you also see when t grows, it gets more and more peaked. Right? So this means that the function tends to delta function. Okay. In the limit. Sine. Yeah, and so it gives like this, right? Okay, and also we take limit of large box, L tends to infinity, so replace then sums with integrals, right? But the rule to replace sum with integral is to take into account that the distance between adjacent modes is 2 pi over L, right? So therefore, the rule is this. I have to multiply it by that. In other words, though, you can think of this as delta k in your discrete sum, right? So and then you have to compensate this times that is equal to 1, right? Okay. So another thing is that the Kronecker delta discrete delta has to be replaced with 2 pi over L d, the Dirac's delta. Finally, okay, let's take, okay, that's only one term that I considered, so I don't, okay. The other term is also similar, that arises from B0 times B2 conjugate, right? You can follow the same philosophy and derive similar expression. So then you remember in nk t, the first term was n0, nk of 0, right? And also you remember that here on the right-hand side I have t, right? So I divide by t. So if I divide by t, there is no t dependence on the right-hand side anymore. Okay, that's good. So I say this is my approximation for n dot of k, right? It's Eulerian approximation for the derivative, right? So in fact, it's kind of interesting. So if you think of nk of t behaving like this as function of time, right? So locally you can have big change in derivative, right? But we're not interested in local changes in derivatives. So we want cumulative behavior. Therefore, this derivative represents only large scale, slow part. It's a filtered part, right? Okay, so it represents slow evolution. And small wiggles in the long run, they don't contribute into anything. And so, putting it all together, we get the final familiar for many of us, the wave kinetic equation. Now deltas already should be understood as Dirac deltas. So this is the wave kinetic equation. So one last comment about this equation, that you remember these n's, the n zeros, the n of 0, right? So from point of view of large scale, from slow time evolution, I derived right-hand side only for t equal to 0. And now I obtained equation, and I'm going to be using it for time of nonlinear evolution. How justified is that? It's justified only if the property, RPA property that I assumed for initial fields hold for this nonlinear evolution. And that property is called propagation of chaos property, okay? And that's not easy to prove, right? So this is something that is hidden and kind of brushed under the carpet, okay? But actually, if I considered evolution of PDF, of joint PDF, then I can study this property, how well it holds, right? So this is just a remark on what assumptions are involved. So it's in addition to small nonlinearity assumption, I said RPA is not an approximation. It's assumption. It's just the initial field I take with this property. But in fact, it is an assumption in the end that this property will hold over nonlinear time evolution. It is an assumption until I prove that taking it initially, it will remain so. Okay, but that's much more complicated task. Okay, so I finished for today. So next time I'll consider solutions, so that the scaling solutions. Okay. Correct.